So for part 1 of our video, we're going to be going over basic integration. Integration is just the reverse process of differentiation, and when you find the integral, you find the area under the curve to the x-axis. So for example, in this curve, if we take the integral of x equals 6, we get the area under the curve like this. The easiest integrals are done by using the general power rule, which is just the exact opposite of the power rule for differentiation. So, if the general function is f of x equals c times x to the n power, in order to take the integral, we first add 1 to the exponent and then divide the whole term by the sum of the original exponent and 1. So, when we take the integral of f of x, which is cx to the n power, we would get cx n plus 1 and then divide by n plus 1. At the end, we also add the constant c to show that the constant is unknown in an indefinite integral. So here's an example with some actual numbers. First we have the function f of x equals 4x squared plus 2x minus 3, which we want to take the integral of. So I'm going to put the integral sign here. First we add 1 to the exponent and divide by that sum, which would be 3 for this first term. So I'm going to have 4x to the third divided by 3. For the second term, we're going to do the same. We'll add 1 to the exponent, 2x squared, and then divide by 2. For the third term, x is to the 0 power, so we will make x present by making it to the first power. And lastly, we will add c to show that the constant is unknown. Next, we have definite integrals. When we calculate a definite integral, we calculate the actual value of an area under a function in the domain from a to b. So if our function is f prime of x, we are taking the integral from a to b. This is calculated by first finding the indefinite integral of the function, which is f of x. Once the indefinite integral is found, the function f of b minus f of a should be found. Find f of b by plugging the b value, which is here, into the function and solving, and then do the same with the a value, which is found here. Next, subtract the value of f of a from the value found of f of b. The resulting number is the area under the entire curve from a to b. Here's an example. We will use the function 3x squared minus 2x plus 5, and we want to find the area under this function from, let's say, 2 to 4, which will be a and b respectively. First, we will find the general function by taking the indefinite integral. So we'll get 3x to the third divided by 3 minus 2x squared divided by 2 plus 5x. We will now solve for the definite integral by plugging in a and b from 2 to 4. We will now plug b into this function to find b after we simplify. to get x to the third minus x squared plus 5x from 2 to 4. So first we'll plug in b. When we plug in b, we get 4 to the third power plus 4 to the second power plus 5 times 4 minus f of a. F of b is then equal to 64 plus 16 plus 20, which just equals 100. And we can't forget minus f of a. Now we will do the same to find f of a so that we are able to subtract the two. We'll have 100 to represent f of b, and then we'll plug in a, which is 2, into f of a. For f of a, we get 2 to the third plus 2 squared plus 5 times 2. We then get 100 minus 8 plus 4 plus 10, which is 100 minus 22, giving us the definite integral of 78. We don't need to include c in our answer since the constants cancel out when we subtract. Therefore, 78 is our final answer, which means the area under the curve from 2 to 4 is 78 units.
Today we are going to learn about the importance of natural log in calculus. First, let's do a little review of natural log. Here is the basic graph of natural log, very basic quick little drawing. And the domain of the function is from 0 to infinity, and the range is from negative infinity to infinity. Also, the natural log function is written in the format as ln of x, which is also equal to log base of e x. And as you've learned previously with a logarithmic function, the same properties apply with natural log. These include the product rule, which is log base a x times y, which is equal then to log base a x plus log base a y. Another property is the quotient rule. And the quotient rule is log base a x over y equals log base a x minus log base a y. And the last property we'll be talking about is the power rule. Power rule is log base a of x to the p power equals p times log base a to the x. So basically, you're taking the p down and putting it in front of the function in order to get p up here. So these are just a few of the properties that we'll be talking about that are used quite often in calculus and other basic math. So now let's do a few examples. Our first example is going to be of the product rule. So with the product rule, I'm going to be given the equation ln 6x, which then I can break up into ln of 6 plus ln of x. Now for our basic example of the quotient rule. When given the equation ln 10 over 9, by using the quotient rule, I can break this up into ln of 10 minus ln of 9. And now for our last example of our last property is the power rule example. So when given the equation ln of x squared, I'm going to get 2 times ln of x, because again, I brought down the exponent in front of the ln. Here are some examples. Example number 1, the derivative of ln of x squared plus 1. What you have to do here is this x squared plus 1 is technically u. So applying the second rule we learned, u prime over u, my answer to this one would be 2x over x squared plus 1. Now for our second example. To find the derivative of x times ln of x, this goes back to the product rule for derivatives. So what I have to do is take my f prime of x times g of x plus g prime of x times f of x. So what that means is that my answer is going to be ln of x plus x times 1 over x, and I'm simply going to get then ln of x plus 1. Now for our final example. Find the derivative of ln of x raised to the third power. So here I'm going to have to apply the power rule that we learned previously. So my answer then is going to be 3 ln of x, and I still have to take the derivative of this entire thing. So with that being said, I can pull out the 3, and I know the derivative of ln over x is 1 over x. So my final answer is going to be 3 over x. Now let's try a harder problem. Find the derivative given the equation f of x equals ln of x times x squared plus 1 squared divided by root 2x cubed minus 1. So the first step is that we're going to want to use the log properties. So we're first going to want to use the product rule. So ln of x plus ln of x squared plus 1 squared, and then here we're going to want to use the quotient rule. So it's going to be minus ln of 2x cubed minus 1 to the 1/2 power. The 1/2 power because we have a square root in the denominator. So now we are going to apply the power rule in these situations where we have an exponent here and an exponent here. So ln of x, now we have to drop that 2 in front of the ln, so 2 ln of x squared plus 1 minus, now we have to drop that 1/2 in front of the ln, so 1/2 ln 2x cubed minus 1. Now we actually have to take the derivative of each unit of ln here. So, as you learned previously, the derivative of ln of x, just x by itself, is 1 over x. For the next unit, you can leave the 2 out front, and now, with this being u, I do u prime over u as we previously learned. So it's going to be 2x over x squared plus 1. And I follow the same rules for the last unit. With this being u, I do u prime over u, so it will be 6x cubed, or squared, over 2x to the third minus 1. Now we just have to simplify all this. So you have 1 over x plus 4x over x squared plus 1 minus 6x squared over 4x cubed minus 2. And this is our final answer. So now that you know how to find the derivative of a natural log function, it is important to know how to find the antiderivative or integral of a natural log function. Really, an integral is trying to get your original equation that you started with. So, as you learned, the derivative of ln of x equals 1 over x. If I were to integrate 1 over x, I would get back my natural log function. So it would look like this. The integral of 1 over x equals ln of x. And the same would be true if I had an ln of u type of function or problem. So let's now do some examples. So when given the integral of 6x over 3x squared plus 2, the first thing you need to do is recognize that you have the derivative in the numerator. Meaning, here I technically have u prime over u. You can look at the problem and see. So, by using u substitution, I can recognize that my u is in the denominator. So, that means then, for u substitution, my u will be equal to 3x squared plus 2. And then the derivative of that would be 6x dx. So I can just plug back in and I'll notice that I have 1 over u du because I replaced my 6x here for this 6x, substituted it in, and my u here is also matching with this u here. So this then will equal ln of u, absolute value sign, plus c, which then I plug back in my u that I have previously during u substitution. So I have ln absolute value of 3x squared plus 2 plus c. Really here, you don't need the absolute value signs because with this function being squared, it will always be positive, but it's always better to be safe and have your absolute value signs. Now let's try a harder problem involving some trig. So given the problem, trying to find the integral of negative cosine negative x over sine negative x. Just like any other problem, you have to start by using u substitution. So in this case, my u, I'm going to use sine negative x. When I find the derivative of this, I get negative cosine negative x dx. This means I can just substitute this in for here. So, in the end, I'll get the integral of 1 over u, and this then leads to me getting ln natural or absolute value of u plus c, and when I plug in my u again, I will get the answer of ln natural log, or ln absolute value sine negative x plus c. And for these problems, it's very important to know your trig identities. So the main takeaways from this video is to remember your derivative and integral rules for natural log. This includes the trig rules, and the number one rule to remember is that the natural log only applies to the -1 power. Thank you for watching.